Good afternoon, everyone. Let's get started with today's class. So today's lecture is on common mode feedback, and first we'll go through what is the necessity for common mode feedback, what is the problem that we are trying to solve, and how do we go about solving it. Now, this is a problem which is encountered in fully differential circuits, okay, or let's say fully differential op amps or OTAs. Now, the problem is this. This is something that you may not kind of see when you're, simulating at the schematic level, or even for that matter at the layout level. This is a problem that you will get only if you are trying to do some corner analysis and you have mismatched corners and so on. So let me explain the problem. Let's start with a very simple differential circuit. And here what do? We usually say that, we know how to generate the, let me just say, let me draw with the NMOS. Okay, right. So we always keep saying that, we know how to generate this bias voltage VB, right? So we say like, somehow we can put a current mirror or something like that, and we can generate this bias voltage such that uh, this PMOS conducts the same amount of current as the NMOS. So here inherently, if you look at this one, right, the idea is that ID3 is equal to ID1 and ID4 is equal to ID2, right? A DC current. Right now we are talking about the DC currents, right? Now uh, suppose let's say you are generating this VB in a way that it is quite fixed. Okay, just assume that VB is fixed. Okay, and what happens is, suppose your NMOS transistors end up being slightly faster. Okay, so if you remember in one of the few lectures at the beginning, when we talked about variation and so on, we said that the PMOS can be fast or slow, and the NMOS also can be fast or slow. So we kind of did something like this is typical TT corner where both NMOS and PMOS are typical. It can come to a point where both are fast FF corner or both are slow SS corner. Let's say this is the NMOS axis and the PMOS axis. Okay, so you can also end up with a scenario where the NMOS is fast, right? Fast NMOS and a slow PMOS, or you can also have a slow NMOS and a fast PMOS. Okay, so these are called as the cross corners, right? And when we say corners, these are the 3 sigma corners. And if you fabricate, let's say 1,000 devices and so on, and if you try to measure the threshold voltage by some means, you will find that any transistor will be somewhere in this space, okay, bounded by these. I mean, basically the 3 sigma of the transistors will be somewhere inside this space. Okay, so that is the idea. So inherently we know that some PMOS and NMOS mismatch can happen. Okay, the PMOS can be slightly stronger or the NMOS can be slightly stronger. Okay, now what happens? Let's take the example when we put it in unity gain feedback. Okay, which is basically for a differential mode, you connect the inputs to the opposite polarity outputs, which ends up being something like this, right? Now suppose, let's consider the case if the PMOS current, let's say ID3 or 4, is greater than, let's say, ISS. This is ISS which is flowing, right? And here you have ISS by 2 and you have ISS by 2, right? This is what it's supposed to flow, right? Suppose you have a scenario where the PMOS is a little faster or something, I mean the threshold voltage is, let's say, a little lower, and the VB does not really track that supply voltage. that process variation. In that case, what will happen? Then M5 will have to go to triode, okay, and M1, and basically what will happen is the output common mode voltage, let's say the Vout CM, will increase. Okay, this is assuming that the R naughts are extremely good. Okay, that is they're extremely large. Okay. On the other hand, if let's say ID3 or ID4 is greater than, let's say, ISS by 2, right? Then what happens? There is too much current flowing in, and therefore the M3 and M4 transistors have to go to triode. Okay. Sorry, this is the other inequality. Just flip the sign. That is ID3 and ID4 are smaller. That is the PMOS current is lesser. Then what happens is this M5 transistor has to move to the triode region in order to support that lower amount of current, right? When ID3 and ID4 are greater, I'm sorry, I didn't pay attention to the inequality sign. If ID3 and ID4 are greater than ISS by 2, right, there is too much of current coming in, and therefore M3 and M4 will have to go to triode region in order to support the lower amount of current that is drawn by the NMOS. So this will result in the output common mode going up, and here I'm sorry, I got the direction wrong. So Vout CM will come down, because if this moves to triode region, automatically the voltage, DC voltage at these 2 points will come down. Here Vout CM will basically go up. Okay. Now this problem becomes more severe when R naughts are large. Okay. Now, when R naughts are not so large, there is another problem that happens. Okay, it's the same problem, but there is another source to this problem. Okay, and this is something that you might encounter when you are designing with the lower, deep submicron devices. Okay, now let us say the V in common mode increases. It is still within the acceptable range. Okay, transistors are all still in saturation. Okay, all we are saying is, if let's say the input common mode voltage, instead of coming at, let's say, 0.6 volt, it is now coming at 0.75 volt. Okay, and let's assume that for this particular topology, that shift is not going to put anything out of saturation. If all the transistors are going to be in saturation, it is within the input common mode range. Okay, but what happens? This will take only VGS that is required, right? So this drain to source voltage now becomes what? The input common mode voltage minus VGS. So basically, if your input common mode voltage increases, right, now your VDS will also increase. And if this transistor M5's output impedance is not very high, what will happen? ISS will also basically increase, right? But your PMOS current is generated by a very fixed voltage, right? Or maybe even if you have mirrored the current and you got it, right? Now the PMOS current now becomes lower than the amount of current that is being drawn by the tail current source, because its output impedance is bad. Now this will result in what? The output common mode going down. Why? Now this PMOS current, right, will have to start, this PMOS transistors will have to compensate by either increasing their drain to source voltage if all the transistors are having poor R naught. In that case, what will happen? The output common mode, right, Vout P and Vout M, the output common mode will start dropping, because this PMOS is now trying to take larger VDS to support the same amount of current. Or the other thing that can happen is basically it can, in the sense that Vout basically can come down. Okay, so this is in general taken as a problem which is there in fully differential circuits. In the case of single-ended circuits, that is like if you have a current mirror load and you have a single-ended output, the current mirror will basically take care of all these variations. suppose NMOS is faster, has a lower threshold voltage or higher threshold voltage when compared to what it is supposed to be. All the variations, even input common mode variations, everything will be taken care of because the current mirror will automatically adjust the bias such that the PMOS current is equal to the NMOS current. But for fully differential circuits, there is no guarantee that the PMOS current will be always equal to the NMOS current. Okay, so this problem can be understood as being two current sources which are trying to be matched. There is a NMOS current source and a PMOS current source, and of course you have some, let me just call it as R out P and R out N to make it very generic, because not only for a 5 transistor OTA, even for a telescopic OTA, this problem is basically there, right? And the higher the R outs, the worse the problem becomes. Okay, so at an abstract level, if you say that this PMOS current and NMOS current get mismatched, okay, then what happens is there is an error current which is going to flow here, which is IP minus IN. Okay, so now if you do a normal schematic simulation, you may not really see these issues unless you simulate the input common mode variation, right? That is the only thing that will show up in schematic. The other thing will not show up unless you do corner analysis, okay, or Monte Carlo analysis or things like that, or only when the chip comes back you will know that this problem has happened. Okay, and this problem is quite severe, that it can basically, this error current which is flowing, right, if IP is greater than IN, what will happen? The error current is positive, and therefore it will try to flow through this resistors, right? And therefore the V out common mode will basically increase. Okay. On the other hand, if the if PMOS current is less than the NMOS current, V out common mode will basically decrease. Okay. Now these variations can go such that V out common mode can either tend towards VDD or it can even go to ground, in which case the op amp is completely non-functional. Okay, or it can reach to such a point where transistors are in triode region and you don't get the gain that you actually expected. Okay, so in other words, to understand it, we can basically say that the error current flows through the parallel combination of R out P and R out N, and therefore the output common mode will basically either increase or decrease correspondingly. Okay, now the higher R outs, the worse it is, which means for telescopic cascodes and folded cascodes, this problem becomes even more acute. Okay, in other words, the output common mode is not fixed properly. Okay, the conclusion is, for fully differential circuits, op amps, okay, the output V out CM is not properly defined. Okay, and typically people say when you have a high impedance node, the output common mode, the DC voltage is not well defined. Okay, so if you look at this particular node, V out P or V out P M node, right, the impedance seen here, the output impedance or the impedance that is seen here is very large, right? You have R naughts in parallel. Okay, so for any high impedance node, the output DC is not well defined. Okay, and in other words, if another way to know whether your circuit meets CMFB or not is basically to see, can you visually look at the circuit and say what will be the DC common mode voltage? Okay. In this case, you cannot say what is the DC common mode voltage because it all depends on the VDSS of the transistors, for which you have to go through some high order device equations to figure out what it will be. Okay, just by looking at the circuit, you cannot tell, right? So such nodes are basically high impedance nodes, and those nodes, the common mode voltage or the DC voltage is very poorly defined or not properly defined, and therefore this problem will occur. Okay, even if you don't see it directly in simulation, unless if you don't run corner simulations, you will not see them, and you will be in for a surprise when the chip comes back to the lab. Okay, so we need some mechanism to properly define the DC common mode voltage. Okay. Some mechanism has to be there, some kind of a feedback circuit which is able to sense the existing output common mode voltage and then try to do some correction, right? In this case, what is the correction that you can do? Either you correct the PMOS or you correct the NMOS, right? So NMOS current. So one of the two current sources need to be corrected, right? And for that, you basically need a sensing to happen and you need a correction mechanism. This is a typical negative feedback circuit which we see in many other scenarios. Okay. So first, let's look at what are the sensing mechanisms. Okay. Okay. So right now, let us say this is Vout 1 and this is Vout 2. These are the two differential outputs that are in your circuit. It can be any kind of an OTA. Okay, 5 transistor, telescopic, folded cascode, gain boosted, 2-stage, whatever it is, right? How do you sense the output common mode voltage, output common mode DC? One of the easiest ways to do is basically to put two resistors, let's call them R. And if you look at the central node, okay, this node, let's call it as V0, okay, you can, how is the differential voltage defined? So this will be some VCM plus VDM by 2 and this is some VCM minus VDM by 2. Now you can do superposition and you can find out that this V0 will be equal to VCM, right? If both the resistors are the same, right, this node V0 will only react to common mode signals and it will not react to differential mode signals, okay, because this node, as long as these two resistors are exactly symmetric. So this is one of the easiest ways to sense the common mode voltage, but then this has a problem. Okay, so let me draw the circuit. For this example, I am just taking a 5 transistor OTA because it's easier to draw and easier to analyze also. This, whatever we discuss, is of course valid for any other OTA. Okay, so let's say this is V0. Okay, this is R and R. Now, although this gives you the value of the common mode, DC common mode voltage, or in general the common mode voltage. Okay, so what happens is CMFB does two things. I will talk about it later. Right now, let's talk about the DC common mode voltage. Let's not talk about the AC common mode. But whatever we discuss is also valid for the AC common mode also. All right. So the DC common mode voltage, let's say this is 0.6 minus something and this is 0.6 plus something. This will be basically equal to 0.6, right? But for the differential signals, right, now what is happening? Let's say this, if you draw the half circuit, right, this resistor, let's say it is used to, what happens is, let's say the other V0 is going to some whatever sensing node. What happens is basically this resistor R comes into the picture of your differential signal. In other words, the R out dash, the new R out becomes the existing output impedance in parallel with this R that you have put. Okay, so which means what? If you don't want this sensing mechanism to affect your actual differential amplifier's performance or your OTA's performance, you need to keep R as high as possible. Okay. Now, in the case of, let's say, telescopic or gain boosted op amps and so on, this value of R will easily reach the range of hundreds of kilo ohms or mega ohms if you want it to be completely out of the picture, right? If R is much greater than R out, then this R does not affect it. So basically, it means that it requires very large area to implement large resistors. Okay. And along with this, what will happen if you have a very large area to implement the resistors? Let's say a poly resistor or something will have extremely high, will have higher sheet resistance, but you will have very large area occupied by this resistors itself, and the other thing is you'll have parasitic capacitance due to this resistors implementation. Okay, so this is a problem. Okay, but still what happens is we will see the other mechanisms, but they also have their own drawbacks, and so many times what happens is that this method seems to be the easiest method or the best method to sense the common mode voltage. Okay, now basically we don't want this resistor, right? Let's look at the second method, right? The second method is basically to try to eliminate the presence of this resistor, because we saw the disadvantages of using this resistor here. Okay, so how can we get rid of this resistor? One way to do it is basically to say, like, let me not load the differential arms with let's say this is Vout1 and Vout2, right? I don't want to directly load these resistors, and so what I will do is I'll just take this, put a common drain stage or a source follower, right? And this will basically drive my resistive divider. All right. So I don't want my resistor to directly touch the output nodes, because that is giving rise to a degradation in the gain and output impedance and so on. So I will just use a source follower, right? And the source follower will drive this resistive divider. Okay, this becomes my V0, R1 and R2. Let's just say R, both are let's say equal. Now this works fine. Let's call it I1. Let's say this is M1 and M2. Okay, these are the differential output arms. This will work fine as long as your swings are less. Okay, let us say your Vout swings become very large. Okay. Let me just say works well for smaller output swing. Okay, so the M2 and M1 are in saturation, and the source follower basically works as expected, right? And we are able to get the output common mode voltage, which is a good reflection of what exactly it is. Of course, it is level shifted, right? It is level shifted by this VGS here, but still, I mean, we are able to detect it with an offset, so that can be taken care of, right? Like we know if the output common mode basically starts going up, we will know it, or if it is going down, we will know it. Only thing, there is a fixed shift, that is okay. All right, but what happens for large output swings? Okay, because many times this is what happens. As the output of the ampere, your swings are enlarged, and as the swings become very large, what can happen? One of these transistors can go out of saturation. Okay, basically you want this, even these current sources I1, they will also be used, I mean implemented using transistors. So all the 4 transistors here need to be in saturation. Let's just say, you can think through it. Let's say if the output swing here becomes very large and this correspondingly becomes very low. Let me just maybe draw this. Let's say it is like this, right? M2 will work fine, right? And but this M1, right, it is gone very low, and therefore things will become your output, it no longer acts as a proper source follower, right? And in fact, the excess current that is coming will have to be borne by either of the 2 current sources, right? Basically your V0 is no longer a correct representation of Vout Cm, because M1 or M2 or I1 sources can go into triode. Okay. And then once it goes into triode, then it is no longer remain. I mean, whatever we have assumed is no longer working. So for large swings, this has this problem. Okay. Now there is another method also that you can use. Basically, if you you don't want to touch this V out line, right? V out 1 and V out 2, right? You don't want to put a resistor directly. So one way to do it is basically to take, another way basically is to say, take these two nodes and feed them to two transistors which are like this, okay, and you connect both their drains, and let's say this is VP. Okay, what are we doing here? We are connecting the two differential arms to a pair of transistors, but these two transistors M1 and M2 are operating in deep triode. Okay, they are sized in such a way that they are operating in the triode region, and sized in that way, and also in whatever is connected to, let's say, VP. Now in the triode region, R on 1 is given by what? 1 by mu n Cox W by L VGS minus VTH, right? So you can write the expression for both M1 and M2. Basically, these two act as what? Variable resistors which are shorted together. Okay. So when this goes up and down and this goes complementarily, what will happen? The differential part will start getting cancelled out. Okay. But whereas the common mode part will still remain. Okay. So you can write this R on expression, and therefore if you look at the R total, you can basically R total approximately can be written as mu n Cox W by L, right? This becomes V out 1 plus V out 2 minus 2 threshold voltages. Okay, R total is nothing but R on 1 parallel to R on 2. So you can write the expressions, and then you will basically come to this conclusion. So as long as they are in triode region, they act as variable gain resistors, and the differential component is cancelled out because the resistance variation on one side is cancelled out by the resistance variation on the other side, right? And the common mode resistor value alone impacts the effective resistance seen between these two nodes. Okay, so you can basically maybe some current or put some resistive divider and basically end up with having a voltage which is proportional to the common mode voltage. Okay. Now here again the disadvantages for large swings. Okay, one of the transistors can enter saturation region, right? For example, let's say this is a very large swing here. Let me use, let's say if the swing is very large, right? So when this is very high, this becomes very low, right? And therefore, when this is very low, M2 will go into saturation, because now the VDS might be higher than VGS minus VTH because the VGS has come down, right? So M2 goes into saturation. So if M2 goes into saturation, then this approximation, then this assumption of this R on is no longer valid, because now it is not in the triode region, it has moved to saturation region. It has the impedance of R naught. Okay, and therefore this does not work. All right, and this node VP basically will react to only common mode signals if the signal swings are smaller. So both method 2 and method 3 work well if your output swings are small, but the moment your output swings become larger, okay, you will start seeing some kind of wrong results coming out of this whole thing. Okay, and that is the reason why many times the first method, okay, where you put a resistive divider, is basically used, and especially for deep submicron designs where your R naughts, your R out is not extremely high, right? You can, especially for 5 transistors OTS, you can basically put a decent amount of R and get away with it. Okay, maybe pay a little penalty in terms of differential mode gain, and then live with, I mean, but still you get your sensing happening. Okay, right. So now that we have looked at how to do sensing, let us now look at how to do correction. Okay, what is the common mode feedback techniques? So again, let's do the simple one first. All right, the simple and elementary one is the one which works really the very best. Okay, so going back to the older circuit, right? Now that we know the common mode voltage, right? This node is the V naught is basically the common mode voltage, right? And if V out CM increases, right, then what will happen? Obviously, V naught will increase. Now, what did we say earlier in one of the earlier slides that we saw? We saw that for if you look at this here, if V out common mode is increasing, it basically means that your PMOS current is higher than the NMOS current. Okay. Now, basically, what should you do? What should be the correction action? You need to reduce the PMOS current. Okay. So, even if it is due to NMOS current dropping down, you need to correspondingly reduce the PMOS current. You just, in this case, what we are going to do is just control the PMOS current. Okay. Now, for this PMOS current to be controlled, what can you do? This node voltage VB has to be controlled. Right. Now, how will you control this node voltage VB? VB can be controlled. So, in which direction should VB go? Basically, if you want to reduce, we need to reduce the PMOS current. If you want to reduce the PMOS current, what you need to go? VB has to correspondingly increase. If VB increases, the VSG drops down and the PMOS current will reduce. And then that will basically solve the whole problem. Okay. Now, if you look at the direction in which VB is going and the direction in which V naught is going, basically both of them are going in the same direction. Okay. So, a very simple way to do CMFB is basically short these two nodes. All right. And basically do your design such that, you will have to kind of do a little redesign, like such that, the W by Ls of the PMOS will sustain for this, will sustain the same amount of current for this new, let's say, VSG voltage. But this is a very simple, effective common mode feedback circuit. Okay. If V out common mode increases, your V naught will increase. Basically, your VB will also increase, and correspondingly, your PMOS current will come down. Okay, and it will solve the problem. Of course, now you can again say that now this is a feedback system, and therefore the loop gain is what is going to determine the amount of correction that is going to be there. In other words, any negative feedback system, the residual error is dependent on the loop gain, and so in this case we have very less loop gain. You can talk about the loop here being this, right? And so you can say that the voltage VB is translated to GM times some current, right? Now I'm talking about small signal again, okay? And that current is multiplied by this resistor R, and that is going to give us the basically the loop gain for this, and therefore there might be some residual error. Okay, so residual error will be there, residual error will exist, but it's usually tolerable. Okay, you're okay. Like if you expected, let's say 0.65 volt and you ended up with, let's say, 0.67 or 0.68 volts, that is still fine, right? Otherwise things would have gone to VDD or ground, but this thing is basically nicely controlling it and keeping it within a range. Let's say 0.65 can go up to 0.7 or 0.72, and on the lower side might go up to 0.5 or something, but still everything is in saturation and things are working fine. All right. So this is a simple way to do. Okay. But in certain cases, right, you might have, you might need a precise common mode voltage. Okay, let's say this is going to drive another stage and you don't have too much room there for common mode variations, or for some other purpose, whatever be it, you want the output common mode to be fixed to a very precise value. Then what can you do? The way in which you can redo the circuit is basically to say, what do you need to do in order to reduce the gain? I mean, to reduce the residual error, you need to increase the loop gain, right? So how can you increase the loop gain? So, I mean, I'm not drawing the bottom part of it, I mean, just to save time. I take this common mode voltage, okay, and I feed it to an op amp, okay, and I put a V reference here, and this op amp is basically going to feed my PMOS bias. So this is also very commonly done. Now let us see what should be the polarity of this op amp. What should be the polarity of the op amp? If V0 increases, right, this VB also has to increase. That's what we saw, right? So which means that this will be the plus terminal because it is in phase, and VREF will be in the minus terminal. Okay. So many times you will see that for good common mode performance, people usually end up using another op amp where it is an op amp with a single-ended output, which will basically stabilize your output DC point. Okay. And as an aside, let me just add a point here. CMFB stabilizes output common mode DC, right? As a side advantage, you also have CMFB attenuates common mode noise. Okay, because till now whatever we talked about as being, common mode signal, if you just replace that with, let's say, a common mode AC signal, this node V0 will also respond to common mode AC signals. So you will have some common mode AC signal also coming in here, and this bias voltage which you provide will also have a common mode, will also have an AC component, which is basically going to act in the opposite direction of this existing common mode signal. So that way, CMFB will basically attenuate common mode noise, and this is also something which is very commonly and routinely used in industries to reduce the amount of noise in all these op amps and op amp based circuits. Okay. All right. So this op amp based circuit can be extended to all the other folded cascode or telescopic cascode and other types of cascode. So let me just quickly draw a telescopic cascode, right? Okay. So there are a lot of ways by which this CMFB is implemented. You can have so many combinations and permutations. Let's say this is VB1. The job of VB1 is basically to improve the, it's to make sure that, M1, M2, let's say this is 1, 2, 3, 4, 5, 6, 7, 8, and this is 9. So to make sure that, M1 is in saturation, M9 is in saturation, and so on, right? Now here this is an NMOS input pair, and the current source is basically, the current source load is the PMOS, right? So the PMOS current is set by this voltage. Okay. Of course, this VB2 also is basically, this does not directly impact the current, right? It has very minimal impact on the current. The actual current is controlled by the, let's say, VB3. Okay. Now again, what can you do? Let's say this is Vout1 to basically not clutter the circuit diagram. Let me just draw it separately. Let's say this is Vout1, this is Vout2, right? You take this and basically give it to an op amp, right? Let's say you give it to an op amp, and this is your reference voltage. Now what is the reference voltage? Basically, even in this case, let's say reference voltage is nothing but the output common mode voltage that is desired. Okay. For example, you want to fix your output common mode voltage at, let's say, 0.65. All right. So if you give that reference here to this op amp, this negative feedback loop will basically work in such a way that it is going to minimize the error between the two input terminals of the op amp, and therefore your output common mode will be as close as possible to the desired output common mode voltage. Okay. So the same way, this V reference is nothing but the VCM desired. Okay, let me just call it as the VCM out desired. Okay, so whatever you give here, of course, obviously there are limits. So this will basically, this op amp will basically drive the either. So there are two ways to correct it. Okay, so let me say one scheme. In scheme 1, V out is connected to VB3, right? Basically your PMOS current is controlled. Okay, so in which case you can see what should be the polarity. So as we saw that, then basically this has to be the plus terminal, this has to be the minus terminal, and this will be given to VB3. Okay, so the PMOS current is basically controlled. You can also come up with another scheme where you are controlling the NMOS current. The V out of this op amp, right, is connected to, let's say, VB4. All right. So if it is connected to VB4, which is basically providing the tail current source for your, it's the tail current source of your NMOS, right? So you are basically NMOS current is controlled here. Now, because it is an NMOS device, if your output common mode voltage is going up, which means the PMOS current is greater than the NMOS current, right? Now, what should happen? Your NMOS current has to go up. So basically, it is the same polarity. So this is your plus and minus, right? So this goes and controls your tail current source. So either of the two methods are possible. Okay, you can either control the PMOS current by reducing the PMOS current, or reducing or increasing, or you can go and control the NMOS current. Okay, so a similar technique can be used for folded cascodes and so on. Okay, whatever be the methodology that you are using, you can again always control the either the PMOS current or NMOS current through this means. All right. Now let's look at one way of, so all these are basically the other point is this common mode V0. Okay, let me just put a point. V0 can be generated through other means also, or let me say other techniques also. What are the techniques? Some of the techniques we saw previously, sensing technique, right? You can either use two transistors in triode, or you use a source follower and put this thing. So any of those techniques can be used. Okay, because especially using this resistive divider directly for telescopic cascode, folded cascodes and all, it will basically go and impact your gain, or you will end up with very large resistor areas. Okay, so you can, this V0 can be generated in any means, and you use an op amp to basically set either the tail current source or the PMOS current source, or however it works in your circuit. Okay, now let us look at another way to do it. Okay. Another way to do it is basically to say that you can use the technique, sensing technique of using triode resistors, right? Let me just quickly draw that circuit. Okay. Let's say this is your telescopic cascode. Especially for telescopic and other cascodes, this technique is used. I'm just giving you one version. The other complementary versions can obviously be done. Okay, so now this is our telescopic cascode. This is our Vout1 and Vout2. Now we saw that putting two transistors in deep triode, it can basically take care of your will basically generate your output common mode voltage. Now this technique basically says that in this technique I'm putting it at the PMOS end, like you can try all the other combinations, that is to control the NMOS current or If you have a PMOS input pair, you can control the NMOS current and vice versa. All the permutations and combinations are possible. Okay, but the concept is like this. Like you put a variable resistor here, all right, which varies according to the output common mode DC voltage. Okay, or let me just say output common mode voltage. Now what is happening here? These two transistors are having a certain, let's say VB1, right? The effective VSG for this transistor is what? VDD minus, of course, let's say this is the VR, this is the source voltage, minus VB1, right? This is the effective source to gate voltage, the VSG of the PMOS transistor. Now by changing this VR, you can control the amount of current that this PMOS current source is going to pump. And of course this second VB is, I mean, if you put it in the comfortable range, this really does not impact your current much, right? We have already seen that in the cascade current sources, right? So VB1, we are not touching VB1 also here. Only thing is we are just putting some variable resistor, a small variable resistor at the source of this PMOS, and that resistor is going to control the source to gate voltage of the PMOS transistor. Okay, and by doing that, we are basically going to control the PMOS current. All right, same thing can be done for NMOS currents also. Okay, or if you have a PMOS tail current source and then PMOS input pair, you can control the same thing on the NMOS side. Right? So how do we do this? Basically, this variable resistor can be implemented by two PMOS transistors here, right, which are basically in the triode region, right. Now these are connected to, oops, not this one. These are connected to the outputs here. Okay, let's say this is Vout2, this is Vout1. These are connected here, just like how we saw in the previous, just some time back. We know that this particular node will react only to the common mode voltage. This, let's say M11 and M12. Okay, M11, M12 are in deep triode. Okay, so this is a very common way to control things. This is also quite commonly used sometimes. Okay, same thing can be done for the folded cascade also. You have that stack of transistors, right? You can either control the PMOS current or the NMOS current. Okay, using the same thing, using the same technique. All right. Now, lastly, let me just talk about CMFB for two-stage op amps. All right. So for a two-stage op amp, let's say you have, let me just quickly draw. I'm drawing only one side. Okay. Now, if the output common mode voltage here, let me say VCM1, if this increases or decreases, it changes the bias for the second stage, right? So VCM1 changing here or there will basically affect what? VCM of 2 also. Okay, I'm just drawing only for one side to save time and clutter, right? So the idea is, if you can look at VCM2, okay, that is like, let's say this is Vout2, and similarly you have Vout1 here. Let's say you somehow sense Vout1, okay, you can do it in any of the ways that we have done. Okay, let's just say you put it through an op amp. Let's say this is VCM2 and you have your Vref, right? Now what you can do is, this, let's say Vout will basically can be connected to VB. All right. So what you are doing here is, you are sensing the output of the second stage, the common mode voltage there, and you are controlling the current of the first stage. Okay, you are controlling the current of the first stage. So this is something that can be done, but this has certain problems. Okay, this will work, but the problem is going to be something like this. Okay, of course, this op amp can either control VB or it can control V tail or anything. Okay, depending on whichever, either you can look at attack the PMOS current or you can control the NMOS current. So however you want, you can basically control. Okay. Now, what happens is if you draw the equivalent circuit, now you can see that there are two stages here. Okay, let us draw the common mode equivalent circuit. Okay, the common mode equivalent circuit looks something like this. Okay, let's say this is M3 plus M4, right? Because this is the common mode we are talking about. Let's say this is M3, M4, M1, M2, and let's say this is M5, M6, and that will be M7, M8. The other side, let me just write M7, M8, and let's say this is your M9. Okay. Now the common mode equivalent circuit is going to look like something like this, right? This is M1 plus M2 because it's common mode. This current source also comes into the picture. This output is going into M5 plus M7, right? And here you have M6 plus M8, right? And this is going into, let's say this is the equivalent common mode resistance that is seen, okay? And that is going into your op amp. Let's say this is the polarity, and this output, this op amp has a gain of, let's say let's just call it as A2, okay? And this is going to either control this or it is going to control the PMOS side. For this example, let's say this is going to control this, right? Now, this is a negative feedback loop, all right? Let us look at the pole locations, okay? Here you'll basically have some capacitance, right? So here you'll have one pole, right? Here you'll have one more pole, obviously, because there will be some capacitance here. Definitely the CL capacitance will be there. Okay, this will be the parasitic capacitance of all these transistors, right? So this will be pole number 2. Okay, this transistor, this op amp itself will be a single pole system. So obviously this will have one more pole. Okay, and many times what happens is this RCM will be high and there will be some parasitic capacitance here. Now this can form a fourth pole. Okay, so typically if you look at this common mode equivalent circuit itself, there will be 3 to 4 common mode poles. Okay, now we will see in the next class, the moment you have more number of poles in your circuit, okay, you end up with instability, right? Because this is a feedback circuit, right? Your phase margin should be positive. That is, your gain crossover has to happen before your phase crossover, or else what will happen at some frequency, this negative feedback system will start becoming unstable and start oscillating. Okay, so in order to prevent that, we have to do what is called as compensation. Okay, so we have to do frequency compensation such that you move one pole very close to DC and push all the poles beyond your unity gain frequency. So that common mode feedback loop, the CMFB loop itself needs some compensation, especially in the case of two-stage op amps. All right. Now there's another way to do CMFB for two-stage op amps. That is basically you put the resistive divider and bias your PMOS for the first stage. Basically use a separate resistive divider for the first stage and you use another separate resistive divider for the second stage NMOS. Okay. All right. So this is your second stage. This is your first stage. Okay. You basically use resistive divider to provide CMFB independently for your first stage and independently for your second stage. Now this will work fairly well, and of course the disadvantage is that you don't get a very precise control over it. Depending on your design, it will go and sit somewhere and it will be fairly tight across variations. Okay, so this is our discussion on or rather a brief but I think we have covered pretty much all the points. You can look at, so all this material is in chapter 9 of Razavi, okay, or what we have been covering for the last few lectures. All of that material is in chapter 9 of Razavi. Next, we'll be looking at chapter 10, okay. You can also look at chapter 13. Towards the end, you will have what is called as a switched capacitor CMFB circuit, but for that you need a clock. So where circuits where clocked systems are there, especially in the in mixed signal systems and circuits, DC D2A converters and so on, there you can use switched capacitor common mode feedback circuit. But for pure analog circuits, you don't have that option. These are the different options that you're seeing, that we can see. And in fact, those who are designing fully differential op amps, you will have to basically do a CMFB loop also. Okay, you might say in simulation it works fine, but then all that will go for a toss when you do a corner analysis. Okay, so with this we'll conclude today's class, and the pending lecture on the step response of folded cascode and rail to rail op amp, and also I will do a small demo of how to design a simple 5 transistor OTA, so that you kind of get some idea about how to go about your designs. So all these 3 put together I will upload as a separate lecture. Okay, and is there a possibility to have a lecture tomorrow? Are you guys free?